Right now, 1,000 miles east of Barbados, a pair of Rutgers University oceanographers are leading a 25-day expedition in the tropical North Atlantic. What they're chasing is a process called salt finger mixing and whether it can keep nutrients flowing to ocean life as the planet and ocean water warms. What they find could matter for the whole food chain. So let's get into it with Joe Bradone and Corday Selden, who join us now from their research ship. What are you studying right now?
Yeah, so we're out here studying how life in this environment grows. The ocean covers about 70% of Earth's surface, and it plays a really important role in regulating global climate. One of the ways that it plays an important role in climate is through what we call the biological carbon pump, through the action of small organisms that live in the ocean. So phytoplankton, small photosynthetic microbes make up the base of the food chain out here. They play an important role in climate change, in climate by taking up carbon from the atmosphere. Right? That carbon can then either move up the food web or be exported into the deep sea where it can grow. So our expedition today is we're looking at how phytoplankton grow and how the physical mixing processes in this particular environment, which are also being impacted by climate change, affect that growth.
Okay, so in that mixing process, right, it's something called salt finger mixing. Joe, can you help us understand what that is and how you're exploring that, how you're studying that on this 25-day expedition?
Sure, yeah. So we have a really awesome interdisciplinary team out here. My team leads the kind of physics side of things, so we study the ocean mixing, and salt finger mixing is this, really weird term, but it's a kind of simple idea. I use two analogies to describe this. You put milk in your coffee and you stir that around. That's called turbulent mixing. But if you put a tea bag in hot water, that tea slowly diffuses out. And so that's called diffusive mixing. And so salt finger mixing is way more on the side of that lower energy diffusive mixing. That's actually really, really hard to measure. But when you add it all up in the in the oceans across the world, it can have a really big impact on a variety of things.
Okay, help us understand why that mixing process happens to begin with and why it matters.
Sure. Yeah. So I use that analogy of the tea bag, but in the ocean where we are right now, it's a really unique location. So we have really warm, salty waters that are on top of colder and fresher waters. And so if you can imagine a little blob, a little finger of really warm and salty water goes down into that colder, fresher water, it will actually diffuse the heat out way, way, way faster than it diffuses salt out. And so it's getting colder, but it's still salty. And so that means it's heavy and it sinks. And the same thing happens with the colder, fresher water going up. And so that's why they call it salt finger mixing. It's kind of these interleaving layers in the ocean that really, really enhance the mixing that happens in like the interior of the ocean, we call it, at depth, that you wouldn't normally find without these kind of unique conditions.
So, Corday, you mentioned warming of the ocean. We know that small changes in the ocean can have massive changes for our planet overall. Why does this matter, and how do the changing ocean patterns impact salt finger mixing?
It's one of the ways in which nutrients can be moved from the deep sea, where they build up, into the sunlit upper ocean. So phytoplankton, the plants of the ocean, just like plants in your garden, they need different things to grow. They need water, they need light, and they need nutrients, right? Like nitrogen and phosphorus that you might add to your garden to enhance growth. So in the ocean, there's plenty of light, there's plenty of water, but there's not much nutrients. Now, nutrients can build up in the deep water. So when salt finger mixing occurs, they can nutrients can be transported into the upper ocean, right, where there's light and where phytoplankton can grow and consequently be consumed by larger organisms.
And I imagine this has a trickle up effect, I imagine, on marine life, yes?
Yes, absolutely, right? So if the base of the food web is doing well, then there's more food for everybody else to eat going on up.
how are you studying this? Because I've read that you have some machinery that's as delicate as a potato chip. How are you studying it?
Yeah, so we're using a lot of different instrumentation. The potato chip reference that you just made, I'll start with that one because it's a really important part of our research effort here. We have two different instruments that do this, but they have these really, really sensitive probes that are on the front of this sort of torpedo-looking tube, and they measure kind of the energy in the ocean, the mixing. And we drop them in the water. They fall down, sometimes as deep as, here's one that you're probably seeing right now. They fall down to sometimes as deep as 1,000 meters, so 3,000 feet, and they'll measure the energy that's in the ocean, the mixing. And then because we're on this huge ship that we can put all different types of instrumentation in to collect water samples, and sort of that's where Corday's team takes over, and the physics side, we wait till we get those measurements back, and then the rest of the team goes and starts on their work.
Yeah, and you two are on a ship right now. We should tell our audience. Just lost a little bit of audio there, but we're going to keep going. Corday, just a minute left. What are you hoping comes out of this study?
We're hoping to understand how important salt finger mixing is in delivering nutrients into the upper ocean. So as the climate warms, we tend to think that there will be the warming of the surface layer will create a greater barrier, preventing more nutrients from coming up through turbulent diffusion, right? That stirring that Joe mentioned in his analogy. We're curious to find out whether or not this diffusive mixing mechanism could offset that.
All right, good stuff. Joe Gradone, Corday Selden, oceanographers with Rutgers University. Keep it up. Thank you so much.
Thank you.
Thank you.